Hello, this is Adam Eason. I'm here to talk about some music. The topic of the video today is going to be intonation and specifically how different pitches relate to each other. So, the thing to remember, a pitch is essentially a wave. That is at its most basic explanation. It's a wave moving through the air. It enters your ear, impacts uh, the the eardrum or the membrane, vibrates that, and a whole bunch of bones start vibrating, and eventually it connects to the nerves in your cochlea, and it starts sending that pulse to your brain. But physically, it's a wave in the air. But it's also a wave on, say, a string or on the inside of a brass or woodwind instrument. So, what I'm going to discuss is, if you have a string, why are the notes where they are on the string? Is it random? Is it judged by distance, or what's going on here? Well, the good news is it's not random. If it were totally random, we'd have a much more difficult time actually playing the cello or the violin or anything like that. Um, but it's not judged strictly by distance either. So if you take my word for it that the first octave on a string, so an octave being this kind of relationship, bom, bom, right? We hear a different register, but somehow to our minds, to our brains, they seem like they're actually the same pitch, right? Different frequencies, same pitch. So the first octave is right in the middle of the string. So just take my word for that for the sake of argument. It would be right here on the 6. Now, if it were distance that judged where the next octave would be, then the next octave, 6 inches here, would be all the way down at the end of the string. This is unsatisfactory for a couple of reasons if you stop and think about it. One is that most instruments that have strings can play far beyond just 2 octaves. Second, we know that stringed instruments have different lengths of strings, and we know that they can also play octaves. And the distance from the point of one end of the string to the octave isn't always going to be 6 inches. So what's happening? Well, in actual fact, what guides pitches isn't set distances, it's ratios. Fractions, basically. 2 to 1, 3 to 2, 6 to 5, 4 to 3 is another one. All of these ratios are used to create the intervals that we hear, the pitches that we hear, and the arrangement that we have them. So, in our case, for the octave, bom, bom, it's not just 0 to 6, it's 12 divided by 2. And then when we want to play another octave up above that, this part of the string isn't vibrating anymore because our finger's in the way on the 6. This part of the string is. So now if we want the next octave up, we have to take 6 to 12, which is another 6 inches, divide that in half to get 3 inches, and here's our next octave. Our second octave is right here on the 9. And then from 9 to 12, we divide that in half again, so 1.5 inches brings us here is a third octave. And then you just keep on dividing it and dividing it and dividing it until it gets so small that our fingers are too big to play the intervals that are available there. So that's the general principle. It's about the interval, or the interval from one pitch to another isn't about the set distance, it's about the ratio from one pitch to the next, right? The comparison of the lengths of string in this case. The length of tubing that that air is flowing through for your brass or woodwind instrument. Okay, so to help prove my point, I'm going to go here. Actually, I'm going to go here. This is a wave simulator, and it's going to simulate not exactly what's going on with a cello string. With a cello string, the two ends are going to be fixed, and you would pluck somewhere in here to get this vibrating. But this will do for for the sake of our demonstration. Here we go. We have a string, and right now it's doing something funky. I'm gonna try and even this out. There we go. Okay, and you can see there's this pattern, there's this wave that's kind of traveling across, right? And the frequency is the number of times you see this full movement from the top to the bottom. How many times that happens per unit of time. I'm not actually sure what unit of time they're using here. Probably seconds is what it usually is. But regardless, it's this oscillation from top to bottom. How many times does that happen in 1 second? And that's going to be your frequency. The amplitude has to do with how big, how powerful the wave is, right? It's the same pattern, but just higher and lower. And I guess, oh, you know what? I bet I know part of what's going on here. There we go. There we go. All right. So here it's much, much more clear, right? You see the top and the bottom. How many times does this pass a certain point in a second? All right. Now, I'm not going to delve too much into the math. If you've ever taken trigonometry, you'll know that this resembles a sine wave. It's not a perfect sine wave because the energy in the movement decreases over time. But that's basically what's happening, is it's a sine wave. And hey, here's this online tone generator that generates sine waves. Okay, awesome. So hertz here is our unit. It's the number of cycles per second, basically the frequency, right? So what we have here is 440 cycles per second with a sine tone, a sine wave. And sine waves, like I said, look more or less like this. Not exactly, but close enough. So here, 440 cycles per second. If I play it, this is what it sounds like. So that's a sine wave with a frequency of 440 cycles per second. And we can get strings to vibrate at essentially this frequency, just like we can get the sine wave to vibrate at this frequency as well. Now, what does this have to do with intervals? Remember, intervals, here it is, intervals have to do with the ratio between one note and the next, not the absolute distance. So if we have 440 cycles per second, and we want the next octave up, if you kind of take my word for it, an octave is a 2-to-1 ratio. So in this case, we would double it or halve it to get an octave. So we'll go up to have 440 and 880 at the same time. Right? Again, you hear that octave equivalency, it's called. You hear the one that's higher, you hear the one that's lower, but they sound like they're the same pitch even though they have different frequencies. So I can have the one side as well. the same thing happens. So if I want a different note, a different interval, I need a different ratio. The ratio for the perfect fifth is 3 to 2. So 3 to 2 would be 440 plus half is 220, so 660 cycles per second. And here's our perfect fifth. All right. So that's why the notes on the cello or the violin or the guitar, that's why the notes are where they are. It has absolutely nothing to do with an absolute distance. It has everything to do with the ratios. In fact, if you look at a guitar, it has frets, right? The frets close to the tuning box where the pegs are, those frets are really big. The frets as you get closer to the bridge, as you get closer to the hollowed out circle in the middle, they get smaller and smaller, right? That's those ratios in action. And it's those ratios which determine where one pitch is in relation to another. All right. So that's intonation in a nutshell. Essentially, playing in tune means getting these ratios to line up as closely as possible. Like if I do this with 664, still doesn't quite sound off enough. Alright, now we can hear it. Now we can hear, it's just not quite. Something's kind of off. And as I move away, there we go. Now you can clearly hear that they're not related, right? That's what playing in tune means. You're trying to get those ratios as exactly as possible. So this video is basically just talking about where these intervals come from, how pitches relate to each other, and it's going to lay the groundwork for future videos where I'll be talking about different intonation systems for things like keyboards or pitched percussion. And I'll talk about like the Pythagorean intonation, mean tone, well-tempered intonation, and equal temperament in later videos. But I just wanted to get the basics out of the way first. It's about ratios, and it's about waves, right? So you'll actually be able to see with the ratios, one wave would be moving exactly twice as slow or twice as quickly as this wave if there were another octave playing. So it has to do with the length of the string, the frequency of the vibration, and ratios. That's what intonation is all about. All right, cool. I'll see y'all next time.